Welcome back to the series. I'm still recovering from my second bout of COVID, so apologies if my voice is a bit croaky. In this series, we're writing the microcode for the SAP6502. We've spent quite a bit of time getting the infrastructure going for the microcode generator and the emulator. We've implemented a number of instructions for load, store, and transfers, but this is where we really want to get the run rate going. This is Indian batsman Yuvraj Singh hitting 6 sixes in one over. For those not familiar with the game, this is the maximum score possible off one over, provided the bowler delivers each ball correctly. Apparently it's only happened 9 times in the history of international cricket.
To make it 36 in that over. That's the full Monty.
Anyway, back to the 6502. Let's see how much damage we can do to this list in one video. Maybe I can add 36 new instructions. In the real hardware, the operands come from the W bus on alternate clock cycles and are stored in the A hold register and B register. The output of these go directly into the 74HC181 ALU units, each of which operates on 4 bits at a time. This means we need 2 physical chips to form our 8-bit ALU. The output from the 74HC181s feed into some 74HC283 4-bit adders. These are used for binary coded decimal adjustment, and then the output of these goes back to the W bus via a 74HC245 tri-state buffer. The most complicated part of the ALU is the binary coded decimal adjustment unit. I went over the function and design of this in a lot more detail in another video, but the complexity of the ALU circuit makes the microcode much easier to write. All we need to tell the ALU is whether we want to adjust for binary coded decimal or not. The 74HC181 has 5 control signals. 4 of them are labelled S0 through S3 and the 5th one is labelled M. Slightly peculiar, but that's what we've got to work with. These mode control signals tell the ALU to perform either an add, subtract, and, or exclusive OR on the inputs. These ALU mode signals come from the controller sequencer, and therefore we have direct control over them within the microcode. To understand how some of these ALU instructions work, let's start by looking at the AND gate. It has 2 inputs and a single output. The output is usually 0, except for when both the top input and the bottom input are asserted. Notice how I use the word AND to describe the function. Memorizing that statement is a good way to remember its function. You might be wondering, if the gate only has 1 output, then how does the 6502's AND instruction work? Well, we actually have 8 AND gates operating independently and in parallel. For each bit, the contents of the accumulator gets transferred into the A hold register. The B register is loaded from the W bus. Usually, the data for this comes from an off-chip source such as main memory. This gets ANDed in the ALU unit. The result is held in the ALU hold register, and then it gets transferred back to the accumulator via the W bus. As I said before, the structure is independently repeated for all of the bits within a byte. For the OR gate, the output is usually 0, except when either the top input or the bottom input is asserted, or both inputs are asserted. The exclusive OR gate is similar to the OR gate except for the last part of the condition. The output is asserted exclusively when input M or input N are asserted, but not when both are asserted. Basically, it detects when the inputs are different. Functionally, the ORA and EOR instructions are implemented in a very similar manner to the AND instruction. The AND instruction is ALU operation 1B, ORA is 1E in hexadecimal, and exclusive OR is 16. One of the big changes I've made with the SAP6502 relative to the actual 6502 CPU is the removal of the adder hold register. Instead, we use this buffer to drive the W bus directly from the ALU, which saves the clock cycle. If you cast your mind back to earlier in the series, remember that we use the emulator to test the microcode, and then we run the same microcode on the actual hardware. With a bit of luck, it all works. For all of these ALU instructions, the microcode is actually going to be very similar. Ironically, most of the effort will be in writing the SAP6502 emulator because we need a full working copy of the ALU there as well. Remember that I like to reuse code as much as possible. This is because 1, I'm lazier and this makes it a bit easier, but 2, it should introduce fewer bugs. The danger, however, is that I might make several copies of the same bug, so I need to be careful about that. I'm going to use the ALU breg code as the prototype for our ALU AND instruction. In this line of code, we assign result to be the A hold register ANDed with the B register. Next, we need to update the negative and 0 flags in the status register based on this result. I'll reuse this code with slight modification for emulating OR and XOR operations within the 74HC181. Just as we've reused this code in the emulator, we can do the same thing with the microcode generator. I'm planning to use the LDA instruction as the main template for other ALU-based instructions. Implementing the AND instruction, we perform a main memory read and load the value into the B register. We copy the value in the accumulator to the A hold register. Then we change ALU op to be the AND instruction. Note that we also tell the ALU to update the negative and 0 flags. We reuse this same code for exclusive OR. We just need to change ALU op to exclusive OR. Simple. Same thing again for the OR operation. We just need to use ALU OR. To start with, I'll just test these 3 new instructions in immediate mode. Unmask them in SAP6502 cycles so that they get executed. Let's see if that works. Excellent. Now I'm going to try my luck and enable all the different addressing modes at once. I'll be happy if this works without any bugs, although somewhat ironically, I'm starting to hope for bugs because it makes these videos a bit more interesting. Here, let's see how we go. And it works. I'm pretty sure I don't have to worry too much about getting enough bugs. That was a little tongue-in-cheek. I'm sure there's plenty ready to bite. The next set of instructions I'm going to look at are the shift instructions. These are called arithmetic shift left and logical shift right. For left shift, we move bit 7 into the carry bit 6 into bit 7, bit 5 into bit 6 and so forth, and we load the bottom bit with a 0. For a right shift we do the opposite. Bit 0 goes into carry, bit 1 goes into bit 0, bit 2 goes into bit 1 and so forth. Then we load the remaining bit 7 with a 0. From a microcode perspective, it's easiest to treat these as 4 different instructions. Arithmetic shift left with accumulator, arithmetic shift left on a memory location, logical shift right on the accumulator, and logical shift right from memory. The rotate instructions are very similar, the main difference being that we use the carry bit to stuff the empty bit position instead of using 0. This lets us do shifts on larger 16 and 32-bit numbers, which we need for floating point operations in BASIC. You might be wondering why we have an arithmetic shift left but a logical shift right in the 6502. Well, it's all about how negative numbers are handled in 2's complement form. An arithmetic shift left is the same as multiplying by 2, while an arithmetic shift right is the same as dividing by 2. Consider shifting the number -8, which is equal to F8 in hexadecimal. If we shift left and all the numbers are in range, then -8 becomes -16 and the sign's preserved. If we shift F8 to the right, we load a 0 into the top bit and the result becomes 7C in hexadecimal. This means -8 becomes positive 124, despite the input number being within the correct range. And that's the reason why on the 6502, the shift left is called an arithmetic shift, but the shift right is called a logical shift. I'll implement the rotate left instruction first, and I'm going to use the OR instruction as the template. Basically, we just need to add a number to itself. I'm going to do a main memory read into the temporary EBL register, and then copy that into B register and A hold. Then I just add these two numbers together, making sure not to use binary coded decimal mode. Simultaneously, we perform a main memory write using the same address, and the output from the ALU goes directly to the main memory. Carry is updated as part of the addition. For the accumulator-based version of the instruction, I copy the value in the accumulator to the A hold register, as well as the B register. I do the same ALU operation, and I save the result back into the accumulator. I can reuse this code for arithmetic shift left for both the memory and accumulator versions of the instruction. The main difference is that I have to make sure that carry is clear in the ALU operation. I do this explicitly by asserting the carry 0 signal from the controller sequencer. This will force the lower bit of the result to be 0. By reusing code in this manner, writing the microcode generator is not actually as hard as it might look at first glance. This code's available through GitHub, so you can have a look yourself and see how it's mostly the same concept repeated over and over again with minor tweaks. Now, you might have seen this coming, but I'm going to use the same code that I used for ASL to implement the decrement instruction. I'll cut and paste this code. This time I do the main memory access and load it directly into the B register. I load the constant value of -1 into the A register. Remember that our constants are 4 bits, but I assign and extend them to 8 bits in hardware. So 0f in hexadecimal becomes ff in the A register. I duplicate this for decrement x and decrement y. I load the value from the index register directly into the B register, and I redirect the output back to the same source register. I need to make sure that I remember not to do this write back to main memory. Copy and paste this for decrement y. Now that that's done, I'm going to take all 3 decrement instructions and reuse them for the increment instructions. That's the increment, increment x, and increment y instructions. All I really need to do is change this constant from being -1 to +1. I enable the new instructions within SAP6502 cycles to make sure they get executed. Let's try this. And no, that seems to be taking longer than normal. I'll kill that process and see if I can isolate it down to a single instruction. I tend to do this like a binary search. I remove about half the new instructions and see if it works. No, then I keep isolating more and more until I get down to a single instruction. I'll compile this and see if it works. No, well, it looks like a different type of failure, but it's still not working. I've gone back to my old trick of directly implementing the decrement code in C++. Now we'll compare the results for both the effective address and the status register from both implementations. It's a little tricky to see here, but the microcode running on the emulator generates a status register result of 34 hexadecimal, while the C code generates a value of B4. This means the top bit, which is the negative flag, isn't being generated by the microcode. The emulator is the problem. I haven't updated the negative and 0 flags in the add with carry instruction in the ALU. That's much better. At the moment, I'm storing the P flag in the status register, but I really don't want this to be visible to the programmer. This is the page flag, and it's usually used during effective address calculation. Instead, I'll instantiate some Boolean variables for both the P flag and the U flag and just keep them hidden. I'll need to update the add with carry command in our emulator, check for a carry out, and update the P flag appropriately. The P flag will be updated on every ALU operation, while the carry bit in the status register is only updated if the update C signal from the sequencer controller is asserted. That's the main difference between these two signals. I also need to update the address calculation for the controller word so that it uses the P flag rather than bit 5 from the status register. Remember that from the programmer's perspective, bit 5 of the status register is always meant to be a 1, and I think there was one game, might have been Mission Impossible, which complained when I didn't do this. Let me try this out. That seems to be working. That's good. I want to start re-enabling more instructions and see how good our coverage is. I'll start with Shift left and rotate left. And no, nothing. Let's have a look at the code. There it is. I need to differentiate the shift instructions on memory locations versus the shift instructions on the accumulator. Try again. Still not working. It looks like my string of 6s has been interrupted. One of the principles I like to use when debugging is to do a visual inspection before doing any functional tests. So let me just have a quick look at these lines of code for ASLA. There it is. I'm still doing a main memory write, even though I want the answer to go back to the accumulator. As I mentioned before, the downside of copy and paste, of course, is that you tend to copy and paste the errors as well. I'll have to go through all the other new instructions and make sure they're correct. Let's compile this, give it a try, and we have a winner. One of the ALU operations that the 6502 needs, but the 74HC181 doesn't have, is rotate right. This instruction has an interesting history in the 6502, because the very first implementations of the hardware didn't actually support it. To handle shift and rotate right here, I'll need to add in another 74HC245 tri-state buffer within the ALU itself. This transfers the output of B to the W bus, but it offsets the bit position by 1 position to the right. This is under the control of the right shift signal coming from the control word. In the emulator, I'm going to add this as part of the ALU BREG instruction. Basically, we check for the shift right signal, and if it's present, we do this instead of the B register pass-through. We take the least significant bit from the B register, and we use that to update the carry bit within the status register. We check to see if we had a carry before the instruction, and we use this, or 0, for the most significant bit of the shifted byte. Finally, we need to update the negative and 0 flags. I'm going to take the ROL and ROR instructions and use them for the rotate right and rotate right through A instructions. This time, I only really need to worry about the contents of the B register because the A register is not used in rotate right. When I do the rotate right from main memory, I read it into the B register, I select BREG as our ALU operation, and most importantly, I assert the shift right signal. I use this to make the rotate right through A, and then I take this pair to make the logical shift right instruction. The main difference is that in the logical shift right, the carry 0 signal is asserted, so the top bit becomes 0. I do the same for logical shift right through A. I'm going to unmask all of these instructions in SAP6502 cycles to make sure they get executed. There are 4 instances of the shift instructions where they operate through the accumulator. Let's give these a try. That looks good. I'll enable all of the shift and rotate instructions with all the different addressing modes. Compile it. Now let's see how it goes. There we have it. I think we're starting to get the hang of these instructions. Of all the 6502 opcodes which have a valid instruction associated with them, I think we've implemented about 2/3 of them already. In the next video, we'll look at branches and jumps, and then the video after that, I'll go over stack operations including jump to subroutine and return from subroutine. I hope you're getting some value from these videos, even if you don't plan to build your own TTL CPU. Seeing how the microcode works should give you a better idea of how these things work under the hood. If you feel inclined, remember to like, share and subscribe, and I'll see you in the next video.